Alright, welcome back again to this video in ABE161. We'll continue our discussion on tributary areas or tributary widths. This video will be doing sample problem, and the sample problem will encounter computations for slabs, slabs to beams, and then beams to girders, or walls to beams, that kind of situations, wherein we can apply this concept of tributary areas. Okay, so for our problem, we have this framing plan. So we have framing plan like this. So we have column 1, C1, C2, that's column 2, column 3, 4, and 5. Okay, so we have beams. So this beam number 1 is connected to column 2 and column 1, while beam number 2 actually rests on a girder. So this one is a girder because it carries smaller beams, so girders, and then the other end of the beam is a column. Now for beam number 3, it is actually supported by both girders. So we have a girder number 2 here. So girder number 2 and then girder number 1, spanning from let's say this is say balloon, so number 2 and then balloon number 4. Okay, and then we have a beam number 4. So we have this dashed line over here. So dashed line just represents that there's a wall on this line right here, and we also have a wall on this portion of the girder 1. So there's a slab actually. So there's a slab on top of the beams, and if we try to visualize this in an isometric view, we get this one. So this is the point A, then point B, and this is a wall, a 100 mm thick concrete, and then on this side as well. Okay, so we are asked to find the let's say the factored loads on each of the structural members. Okay, so we'll label this as, okay, so this portion right here, let's just call this is S1 or S-1, meaning slab 1, and then we have slab 2, and then slab number 3. Okay, so it's not yet the one-way or two-way, it's just the it's just a label. Okay, and we're given with this loading. So dead load, floor dead loads, we have 2.6 kilopascals. So let's assume for now that this is the total dead loads. Okay, so there are still other terms. Later on you'll encounter that there are terms like superimposed dead loads. So meaning that other than the dead load or the dead weight of the structural members itself, there are still dead loads, like for example the ceilings or the electrical facilities, electrical service, and if there are, let's say, plumbings or pipings and stuff like that, then there's another kind of or another value you have to add that up in this in the dead weight of the structure. Okay, so for now let's just assume that this is the total dead load. Okay, and then we have a dead load for the wall, so 0.034 kilopascals. So where did I get this? This is from a data, and for now I just give it straight to you, but in our homeworks then you have to find that one out in the tables. And we have a live loads of 1.9 kilopascals. Okay, so let's solve the structural loadings of each member. Okay, so this is our solution. So let's say number one, step one, or the first step we will do, we need to solve the floor ratio. Floor ratio. Okay, so we have S1 and we have a ratio of Ly over Lx. So that is, okay, so this is our slab number one, and we have a 6-meter length and a 4-meter width. So that's going to be a 6 over 4 meter, which is 1.5. So this is less than or equal to 2. Therefore, this is a two-way slab. Okay, for S-2, we have a ratio of, okay, so 6, we have a ratio of 6 meters and 2.2 meters. Okay, so 6 over 2.2, we have 2.7, which is greater than 2, and therefore that's a one-way slab. Okay, and then lastly, for the slab -3, we have 6. Okay, and the width is actually 2.8. So 6 all over 2.8, that's 2.1, which is still greater than 2, so therefore that's a one-way. Okay, so the next step, okay, so let's just write step number 1. Then the next step, we can solve for the factored loads. Okay, since most of the beams will be will have their loads coming from the slab, so we can solve for the factor loads. Okay, so solving for factored loads. On floor. Okay, so we have this U is equal to 1.2 dead plus 1.6 live. You can also try U is equal to 1.4 dead, but the value would just be less than. Okay, so 1.2 times, what's the dead load? We have 2.6 plus 1.6 times the live load of 1.9. Okay, so take note that we didn't include the wall for now, because we'll have it separately. Okay, so what we'll do here is actually we'll solve in order. So we'll solve the B1 first, and then the B2, the B-3, the B-4, and so on. Okay, so we'll need this data, and if we solve this, we get a value of 6.16 kPa. Okay, so now let's solve for B1. Okay, solving for B-1. Okay, so if we try to draw the B-1, okay, so this is our balloon A, and this is B, and this is the balloon number 1. Okay, so the slab number 1 is a two-way slab. So if we try to draw that, So that's gonna be okay. So this is the loaded area. We have a distance of 6 meters, and then we have a distance of 4 meters. So this distance actually is, of course, that's going to be 2 meters. Okay, so let's solve for the tributary width. So actually, if we try to draw this, what we get is right, so something like this, for example. But we will just use a tributary width concept. We'll apply the equation for the tributary width. So this is our tributary width, and the value of this tributary width is, so if we apply the formula Lx all over 6, 3 minus Lx all over Ly squared. So if we substitute the value, we have 4 over 6, and 3 minus Lx, that's 4 over 6 squared. We get a value of 1.7 meters. Okay, so you notice that our tributary width is 1.7 instead of using the 2 meters. Okay, so we'll use this because the goal here is actually we want to transform these loadings into a distributed loads. So if that's going to be a distributed loads, then what we need, the unit that we need is kilonewton per meter. But since our live load and dead loads, they are given in kilopascals, kilonewton per meter square, then we need to multiply that to our tributary width in meters so that we can obtain this unit. Okay, so let's now solve for factored loads, in terms of distributed loads. Okay, so we have omega u, that's actually ultimate distributed loads or something. Okay, so that's just u, our factored loads here, 6.16 times the tributary width. Okay, so we have 6.16 kilonewton per meter squared times our 1.7 meter. That's 10.5 kilonewton per meter. Okay, so we'll try it here. So this 10.5 distributed loadings is, or refers to this loads, right? So 10.5 kilonewton per meter. Okay, so once you have these loadings, then you can solve for the maximum shear and the maximum moment. And of course, you can also try the indeterminate structures like fixed supports. You can try that one out and use the software to solve for the value of shear and moments. Okay, so the next step would be solving for, okay, so let's solve for B-2. Okay, so for our beam B-2, we have this loadings. Okay, so we have a loading, a trapezoidal loads, and then okay, so we have a trapezoidal load here because this is a two-way slab. But on the slab number 2, we have a one-way. So we have a rectangular loadings here. Okay, so let's just okay, so of course, since this is a trapezoidal load, we'll use a reduced equation. That's gonna be the tributary width for this part, and then another tributary width for this is actually just Lx divided by 2. So the tributary width here, that is 2.2 divided by 2, so it's just 1.1. Okay, so 1.1 meter. Okay, so what's the tributary width? So tributary width, if you apply this equation below, if you apply this, that's actually the same as 1.7. Okay, so our tributary width, our total, okay, we'll write it down here. So we have a 1.7. Okay, so we have a 1.7 plus 1.1, and that's going to be 2.8 meters. Okay, so now we can solve for the distributed loads, or factor distributed loads. That's going to be 6.16 kilopascals times 2.8 meters. And we get a value of 17.25 kilonewton per meter. Okay, so for the next, solve for beam number beam dash 3. So we have a one-way loading on the top side, and then another one-way loading from the bottom side. However, we have okay, let's just draw it here. We're solving for beam dash 3. Okay, so this is our balloon number 3, and this is our balloon A, and then we have a balloon B. So we have a loadings. Okay, so we have loadings here. Okay, so our tributary width on the top side, our tributary width here, that's just 2.2. Okay, so this is our distance from this member to the adjacent member. So we have 2.2 divided by 2, that's just 1.1. And then on the bottom side, we have a 2.8 divided by 2, that's just 1.4. So the value here is 2.5. Okay, so we can now solve for the loadings. So loadings will just simply be 6.16, that's in kilopascals, times the 2.5, and what we get is 15.4 kilonewton per meter. Okay, so the next we'll solve for the B-4. So take note, for the B-4 we actually have a slab, a loadings from the slab. It will carry loadings from the slab, but also it will carry loadings from the wall, since we have a dash line here. Okay, so if we try to illustrate that, okay, so step number 6. This is step number 6, solving for this B-4. Okay, so if we try to illustrate this, this is our B-4, and then this is our, let's just say this is our slab, and then this is our wall. Okay, so the loadings, there's going to be a tributary width. Okay, so this will be the direction, and then we have another loadings from the wall. Okay, so if we try to visualize the loading diagram, or let's say the beam diagram, it's something like this. So we have a loadings from the floor, then you can also can superimpose another loadings from the wall. Okay, so this wall, then this one, the floor. Okay, I mean for the dead load. So and then we have to account for the live loads and solve for the total factored loads. Right, so now let's solve for the dead load of wall. Okay, so D wall, we're actually given with this value. So we have value of 0.034 kilopascals, kilonewton per meter squared. Again, we need to transpose that to kilonewton per meter. So we need a length dimension to multiply that to this value so that we can get a kilonewton per meter. So what the question is, which length value? Is it the height, is it the thickness, or is it the length? Okay, so if you notice, we have thickness here. So a thickness is actually already given, and that depends, you know, the value right here, that depends on the thickness. For example, you have a concrete wall that's 150 mm thick or 200 mm thick, so that this value will be different. Okay, so the thickness is already given. Okay, so that's 100 mm, and the value is this. For the length, it's not the dimension that we need, because that's actually the line of distribution. So meaning what we need is this dimension, the height. So let's multiply this 0.034 kilopascals times the height. So what's the height? In this problem, it's given 3 meters. So 3 meters. So let's label this. This is the height. Okay, so we get a value of 0.102 kilonewton per meter. Okay, so another dead load that we need. So dead load from the slab. So from the slab, we have a value of, okay, 2.6 kPa. Okay, and we need to multiply that to the tributary area. But what is the tributary area for this beam number 4? So again, it's just the halfway of 2.8. So 2.8 divided by 2, you get a 1.4, right? So times 1.4 meter, and what you get is 3.64 kilonewton per meter. Okay, so you can solve for the total dead. Okay, so D total is just simply the D wall plus D of the slab. Okay, which is just 3.742 kilonewton per meter. Okay, and then we have the live load, which is 1.9 kPa, and we need to multiply that to the tributary width, which is 1.4. So we get a value of 2.66. So therefore, we can solve for the factored loads. So factored loads is just 1.3 dead plus 1.6 live. So we get a value of 8.77464. That's in kilonewton per meter. So again, you can also check if you'd like to check the combination of 1.4 dead. Okay, so take note, this is the load combinations that we use more often in this problem, because we only have the Elvis and Blackbox. But if you have other load combinations, loadings, then you have to check other load combinations. Okay, so on step number 7, let's solve for this is already solved, so the B1 is okay, the B-2, B-3, B-4, then we'll solve for B-5. Okay, so B-5, solving for B-5. Okay, so our beam diagram would look like this, or let's say the framing plan will look like this. It's a triangular load. Okay, but then again, what we need is a reduced value. Okay, so this is actually 1. So the balloon 1, then the balloon 2, and this is A. Okay, so the value of this tributary width, if it's a triangular load, it's just Lx all over 3. Okay, so we can solve now. So we have the tributary width. If you solve that, Ls all over 3, that's just 1.33 meters. Okay, so we can now solve for the factored loads, so which is just 6.16. So again, we didn't solve this because since this is just loadings from the slab, then we can use this value 6.16. The previous beam that we solved, we didn't use the value 6.16 simply because there's another loads, dead loads coming from the wall. Okay, so let's continue. 6.16 kilopascals times the tributary width, that's 1.33 meters, and we get a value of 1.4. we get a value of 8.19. That's kilonewton per meter. Alright, so I guess my time is up. I'd like to continue this sample problem in the next video. Okay, so see you in the next video.